All right, thank you very much. Really quick, thanks to Mike and Jacob and all of JSLA for sponsoring my trip out here. I'm very happy to be here tonight. So the title of my talk is Decentralized Databases and the End of the Web Host. So the topic of this talk is a project called Secure Scuttlebutt. It was created by Dominic Tarr early in summer of 2014. I joined it in August of 14, and the two of us have been working on it pretty consistently since then. Now, Secure Scuttlebutt is a decentralized and distributed database which works on user devices and synchronizes in a peer mesh. And so in the course of this talk, I'm going to give a background and a set of technical reasoning for how this project came to be. And then I'm going to give an overview of how it works and how we think it can be put to use. So let's get started. Web services are not free and open source. Now, the web uses a whole lot of free and open source software. You use things like Postgre, Redis, Nginx, Apache, right, on your back end. Front end uses a whole lot of libraries and frameworks which are free and open source, but the web itself is not. The service deployments are closed and proprietary. Users cannot audit the source code of their services. You can't access your data in its raw form, run free queries on it, or modify it. And I think even most importantly, you cannot push changes to a service that you use. So by no charitable definition does a web service fit free and open source. The immediate response to this tends to be, well, what about self-hosting? You can run your own service. Self-hosting doesn't really solve this problem for us because the web is not created equal. People use Facebook. They're not going to use your private deployment of some Facebook clone. So some of the web matters more than other parts. And it's the web that people use that we want to have access to. The inevitable result of this is that the users lose. We lose opportunities to innovate by modifying the software that we use to make small changes that we think can improve on it, sometimes even big changes. We have no control over the policies for our data. We're not able to choose who has access to it or whether or not it's sold. And we lose an opportunity to police our communities, to do things like deal with trolls, deal with spam, or handle naming policies. So we're in a situation right now which is largely minority control. There's a few companies that tend to run the majority of the web. In an interview that Linus Torvalds gave, this was a 10-year retrospective on Git, he gave this quote: "The big thing about distributed source control is that it makes one of the main issues with SCMs go away, the politics around who can make changes. BitKeeper, which is a distributed system, showed that you can avoid that by just giving everybody their own source repository." Now, what is he talking about with the politics around who can make changes? Well, if you're dealing with a traditional host-based source control system, which you can call single authority, you actually have one computer, which is the single host of the repository. And any time that you make, if you think with, for instance, SVN, when you make a commit, what happens is that your machine will create a connection to that host, to the repository host, and negotiate the commit process between those two computers. It's easy to forget that because we've used Git for a while where you're able to make local commits. But in SVN, you're actually going to make contact with the host every time. So this actually creates, well, it's not a problem if you have a company with a hiring process and a relatively static organization. What you have to do is create accounts for everybody that's in the organization and set their read and write permissions. Not a big deal if you're in a company, but for a large project like Linux, where people can come in pretty freely and start to make commits, you begin to run into this question of, well, who does get an account? Who's going to have the access to the repository and what's their rights going to be? And at a large enough scale, this becomes a political problem. So this is what he was facing. Now, why does SVN bother with this? Why do we have host-based solutions in the first place? The reason to do host-based, which is, again, single authority, is that it solves very complex questions about concurrency. When you have a lot of developers working on the same source code at the same time, you need to make sure that the commits that they provide to the source code are going to come into the same order and result in the exact same final output. And when you have a lot of computers working at the same time, this is actually fairly complex because you have no way to set a total order. The single authority model basically solves this by having everybody channel through the same computer. And so then that computer is able to decide what order things happen in and what's the correct state, and it can detect if there's some kind of conflict which has occurred and whether or not the developer needs to back up and deal with that conflict before changing the repository state. All right? So that's why single authority tends to be used. Now, Git is a distributed authority SCM. In this model, users can clone the repository to their local device and freely make commits there. And then they can send it back to the host repository if they like, or they can replicate their changes out to other devices in a peer-to-peer network. But importantly, there's no designated central authority. All of the devices in a Git network are basically equal. And this solved, of course, the political problem that Linux was facing. Now, how does Git do this? Mainly through content hashing and key pair signatures. Content hashing is a way to basically create a unique number for a blob of content. And it is similar to, it's a similar concept as the checksum. The interesting thing about a content hash is that it verifies the integrity of what it is meant to represent. If you have a content hash for a blob, you can check and make sure that the blob itself is correct by comparing it to the content hash ID. And so Git uses that to provide integrity to the database, or excuse me, to the repository. On top of that, it uses key pair asymmetric key pair cryptography to identify the users. So you don't need any single host which is going to manage all of your accounts. You can freely create key pairs and then use the signatures created by these key pairs to identify changes by individual users. All right? So this removes the need to have a single authority. Now, the problem that Linus Torvalds was dealing with is similar to what we're dealing with now, which is the political question of who can make changes. He was dealing with the source control, but what we're dealing with is the web services. So can we apply this basic idea to what we're dealing with now? He's talking about distributed source control and giving everybody their own source repository. So perhaps we can have a distributed web service where everybody has their own deployment of the service. And so that is what Secure Scuttlebutt is. It is a distributed web service, and specifically a data layer. And it lives on every user's device, runs independently of any central authority, and provides basically the same service that a central service would, but without the host. So that's the background to this project and how it came to be. Now let's talk about how it works. The basics are very simple. Users publish JSON feeds. Feeds are followed socially. And synchronization occurs in the background. So every user has their own feed. It is very free form. The only requirement is that you publish JSON object, but there's no restriction on the schemas themselves. We limit each message to about 1 kilobyte each. That's so that whenever you're downloading a feed, if you know there's 1,000 messages on it, we can predict the amount of data that is going to be downloaded. So it keeps the feeds reasonably small for a given set of messages, but otherwise it's fairly free form. Users follow each other's feeds socially, very much like Twitter or like RSS when you subscribe to an RSS feed. And synchronization occurs using a gossip protocol. The gossip is able to work over the LAN or over the internet In fact, the software we have now will discover using multicast UDP. We'll discover peers that are on your local area network and automatically begin to sync with them using the gossip protocol. To synchronize over the internet, we use something we call pubs, which I'll explain in a moment. Now, gossip is a highly caching protocol. What that means is that it's fairly trivial for a single node to basically rehost a feed on behalf of somebody else. So if Alice sends her feed to Bob, Bob can then host Alice's feed to Carla, right? And this helps us get what you call a transitive connection. Because of Bob in that scenario, Alice and Carla are able to connect to one another, right? And so that's how we can get a large amount of connectivity through the network without necessarily having direct connections. This is useful because the internet doesn't provide a really good experience for creating direct connections between user devices. You have to deal with things like network address translation and firewalls. So to deal with that, we have some users which we call pubs. And these are just users that are on a public IP address. They may have a domain name. They don't have any special software. They're simply users. But they're basically bots. And they act as mailmen for the system to be able to bridge different home networks and office networks. So that's really the basics of this protocol. JSON feeds that the users publish. Feeds are followed socially. Synchronization occurs in the background. All right. So for this to work, we have to give a couple of guarantees on the protocol. Those guarantees are monotonic progress of the feeds, provable authorship of the messages, and that history of the feeds can never be changed. Okay? Monotonic progress is the idea that basically there's only one thing you can do to a feed, and that's add to it. All right? So every feed, you can also call it an AppendOnly Log. There is no sharing of the feeds between users, so there's no chance of a conflict. Once you say that message 5 exists and that it is of this content, that is always going to be message 5. Nobody else could ever contest that, right? One user, one feed. Now, every feed has a key pair, which we generate when the feed is created. And on the initial message for that feed, we publish the public key. That's what we call the init message. Thereafter, well, including the first message, and then every message afterward is signed using the private key. So when a node receives a message for a feed, it verifies the authorship by comparing the signature to that public key. If the signature does not match up to the public key, that message is simply rejected. The final guarantee is that the history cannot be changed. This is important so that you know that everybody is basically on the same page, right? You don't want to have multiple versions of your feed existing in the network. So the way that we do this is by basically creating a chain of checksums. Every message includes the content hash of the message previous to it, all right? And whenever a new message comes in, that previous hash is compared against the message prior, and if it does not match up, the new message is simply rejected, right? Now, the purpose of this is to make sure that nobody could ever try to change their history after they've published. Were you to try to do that, were a new message, let's say you've published messages 1 through 10, you try to change 5. Were message 5 to show up, the signature that you have on it would agree, because you're the rightful owner of this feed. But this chain of checksums would not agree. All right? Message 6 already knows what the hash of the message 5 is. And the hash of this new message 5 doesn't fit, right? So this new altered history that you try to push out won't be received. Now, if somebody has not seen your history in the past, and so accepts this new history that you put out, you've basically created a branch of your history in the network. This is an extremely undesirable situation. because your feed will no longer be able to make progress in the network. Some people will have the old version, right? So as long as two versions exist, one of those versions is not going to be able to make progress. So there's a strong disincentive to ever try to change your history. Because if you do so, you may end up in a situation where users are not able to receive new messages from you. As a result, you'll have to abandon the feed and create a new one. So those are our protocol guarantees. Monotonic progress, provable authorship, history can never be changed. Okay. Now on top of that, we have a couple of conventions for how the messages work. We call them conventions because you don't necessarily have to adhere to these, but they're useful, and we use them for creating indexes to be able to search through messages more simply. The first is that messages are typed. This is simply a type attribute that's inside the JSON object. It's a string. We don't do anything with that string except create. We have a function that says get messages of type, right? So it's just a way basically to narrow down. Now, in practice, you use that to set schemas in the application usually. But there's nothing in the protocol itself that decides how schemas work. It's purely conventional. The other convention is that we use links in this system, and the links are content hashes. Three sorts of links that we use: links to user feeds, links to other messages, and then links to blobs, just file objects, right? And these are how they're defined. Feeds are referenced by the content hash of their public key. Message links are the content hash of the message itself. And blob links are to the content hash of the blob. So that is pretty much everything you need to know to understand how secure Scuttlebutt works. Again, it's a very simple JSON feed synchronization protocol. But with these couple of guarantees, we can create a well-ordered network. Now, let me show a quick application. This is called Phoenix. This is the application that ships with the secure Scuttlebutt implementation. And this is basically a simple Twitter successor. The reason we chose to make that as our first application is simply that it maps very closely to the data model that secure Scuttlebutt uses. And so what we're looking at here is a set of posts that people make. I'll switch over to the all data view, and so we can see basically every message of the feeds that I follow aggregated into this view here. And you can see threaded views of the conversations and make replies and what have you. Now, I actually don't have my Wi-Fi on right now. So this application is being hosted locally and using my local copy of the Scuttlebutt database. So that illustrates that you're using a local service, so network connectivity is not necessarily required to use the network. If I were to make a post now, why don't I go ahead and do that? That now exists on my local device, and as soon as I get network connectivity again, I'll synchronize with everybody, and they'll receive this new message. So that pretty much covers it. I have some different topics I can continue to go on with. I made some slides for, but otherwise that covers the basics of the project. So thank you all very much.
How do you discover and/or connect to other users on the system?
So there are two ways that occurs. The local area network, we use UDP to discover peers that are locally available, and we automatically connect to them and begin to synchronize with them. For the pub users, we publish messages saying that there is a pub available at some address, right, at securescuttlebutt.com. And as soon as you see one of those messages, the client will automatically begin to synchronize there as well. Now you have a list of feeds that you have chosen to follow. And so those are the feed IDs that you have this list of, right, which is the hash of the public key of those feeds. And so anytime that you gossip with one of these peers, whether it be on your LAN or one of these pubs, you send your list of subscribed feeds and receive any new messages they have for those users. Yeah?
What's the convention for dealing with forked history? Like, is there any way to invalidate like, a feed in the network, or?
You are actually able to publish quite a bit of information about other feeds by publishing a message which links to the feed that you're describing. So if you were to find that a feed has begun to try to forge its own history, you would be able to publish a message flagging it, possibly stating why that you noticed that it has done this, and recommending that other people stop following it. Yeah.
In this decentralized system, you're trying to eliminate the vectors, essentially, right?
Yes.
So are there any additional security issues that you're using essentially every other computer or node to serve as a server to somebody else?
Well, security is a pretty broad topic. Are there specific issues you have in mind?
If you compare it to the existing model that we have right now, which is Webhost, are there any additional security issues that we should be concerned with?
Well, there's a topic maybe of data privacy. How do you secure your own information? And why don't I jump over to the slides I have for this. SSB right now is public by default, right? Anything you publish on your feed is going to be available to everybody to see. We're working right now on our transport level encryption, and soon after we're going to have end-to-end encryption, right? So the key pair distribution is inherent in the protocol. And so once we have, we will eventually work in one-to-one private messaging using the public key pairs to encrypt, right? And then in the future, we'll be able to pass around symmetric keys to have groups of encryption, right? And so that'll be the basis of any privacy in the system.
Do you have any, so I find that really interesting. One thing I'm curious about, you have all the information, and it seems like this works great, but what if you want to query the system? Like, do you have any thoughts about how you would extend it eventually so I could query a piece of information across many feeds, especially once you start talking about private information, which I find really interesting.
Yeah, well, it does become a little bit more complex once encryption gets involved. Why don't I have a slide for this, in fact. Let's find it here. So the way you could think of the secure scuttlebutt structure is log-based, which is similar to how Apache, Kafka, and Samza work. This is kind of being called right now the Kappa architecture, which is a kind of a neat idea. There's been some talks on that, which I would actually recommend checking out. But the basics of it is that you're going to pipe the log into view processors, right? Into functions that are going to receive the messages and then create a computed state, right? Okay. So to get a kind of more concrete idea of this, that's a view processor up on the top. You're going to pipe the stream of messages into that function, and then it's going to update state in some way, right? So in this scenario, we're creating profiles for each other, and each time you see a message that sets the name, we update the profile, right? Now, there's kind of two broad ways you can work with that. One is to build CRDTs, which I'm not going to get into right now, but it's a form of distributed data structure that you can build on top of it. If you wanted to have really flexible querying on top of it, you could basically pipe that data into something like Postgre and run SQL queries against it. So basically, you would translate new messages into insert statements, and then you would have this view to go against. The version of oh gosh, what is it? We have an application now called Scuttlebutt, which is an implementation of secure Scuttlebutt, and it includes a couple of different query functions that are fairly broad, but which are able to do a fair amount. And that's like get messages by type, and also get messages by links, things like that.
first of all, very cool project. Thanks for the talk. Second of all, what similarities does this have to CouchDB? I mean, is there overlap there in CouchDB's distributed syncing and replication?
CouchDB is a mutable document store. This is an immutable log store. CouchDB, this is an immutable log store. The feeds. CouchDB is meant to be used within a bunch of computers that are run by the same people. So one organization. And Secure Scuttlebutt is really focused towards multiple organizations being able to synchronize with one another.
So I guess going back to the Git analogy, one of the common operations on Git is to be able to, I guess, publish drafts. So like maybe you might create a patch with some changes, and then someone will give you feedback, and maybe you publish information that's embarrassing or unintentional, and then you rebase and you push those changes. Or similarly on Facebook or Twitter, you delete tweets, you delete posts, you edit posts. Is there I guess apart from pushing a new post that says like this is edited, is there any way for users to take control of data that they've inadvertently pushed and say take this back or delete it without users?
Like, is there branching?
No.
Okay.
This is a good time for my complexities slide.
Just one note, Facebook does not allow you to edit posts. They actually create new ones.
Okay. I think they used to, but I mean the point is, can you
The
edit
actual
posts? from there?
record has a new ID
Okay.
when you edit the post. So literally they create new ones and replace the previous ones with it.
Yeah.
How's people forward feeds?
Sorry? Okay. Yeah, you can't, once something is published, if it has been replicated off of your device, there's no pulling it back. And this is admittedly a complexity that is going to have to be dealt with by the application developers. And here are some of the other complexities we have to deal with. Key pairs aren't shared between devices.
But that's like posting anything to any website. Like by the time you posted it, just assume somebody's taken a screenshot.
Yeah, that's sort of the same idea.
So the real strength is that you've eliminated this idea of like ephemeral. It's now gone. So I'm just, and it was clearly, it seems like it was clearly done by design. Like what would you envision being a future product that would really take advantage of this? Like, are you thinking of like politicians speaking and us keeping a document stored for Library of Congress? Like, I'm curious, what would be the end result?
Well, then I have a slide for you. So again, really, for me personally, my interest in the project is to have user control over your application stack, right? So that you can be able to change your software. And so the first step is bringing the database onto your device so that you can then change the software around it as well, right? The list here is meant to point towards the multiple possibilities, but what is really interesting to me, for one, is actually code deployment is one interesting opportunity, since you have every message signed, and we use content hashes fairly consistently. So one of the interesting things you could do is publish code on this system and then be able to have other people sign off on the code and verify that it is not malicious and that it does what you expect it to do. So that's actually one of the more interesting applications that we're looking at now. Kind of importantly, currencies like cryptocurrencies would probably be a poor choice for this, because we don't give a total order for the system, right? Which is what things like Bitcoin are trying to achieve.
One more right here. Yeah. So you mentioned you're using UDP for the discovery part of the application. How can that tie in in comparison to something like the WebTorrent protocol. That's a pretty new thing that's starting to be worked on. That's a very, very, very similar type
Yeah.
of thing here.
Yeah, we're interested in the WebTorrent protocol. It serves very different purposes than what we deal with. WebTorrent is particularly good for blob exchange, of course. But there's also an extension to the BitTorrent protocol that's being looked at right now that uses the DHT inside of the trackers basically as a generic key store, which would be mutable. And so we are interested in integrating with it in that regard. Now, how it's compatible with the two, the protocol is completely separate, and so they would run parallel to one another.
Very cool.